want to give you a brief summary of where we were last time for those of you who may not have been with us here. And I'm doing it a little bit differently than I did. I was using my laptop, but I have a lot more freedom and flexibility with my iPad. And I was able to now get the iPad to work properly so I can do the keynote presentations. This gives me many possibilities because I can do wonderful things like this and zoom in on that sort of a thing and then go back there. And so it's nice. I couldn't do that with the laptop. So I'm going to give you a brief summary as to where we were last week and move on from there. This is a presentation on science, faith, and reason, 4 fundamental features of the world. And those fundamental features we began to look at last week included first the evidence for the universe's beginning. And this is an incredibly important one, as we will see in just a moment. And then secondly, and what we're going to be exploring this morning, is the evidence for the fine-tuning of the cosmos, which keeps on multiplying, keeps on growing. And the third is going to be the nature of biogenesis. How did you get the first living cell? As it turns out, there aren't any simple cells. There are no simple cells. Every cell is as complex as a whole city that we could develop. And the more we look at it, the more elegant it becomes. And then fourth is the nature of information. And that we discover is more and more elegant as we go as well. So the more we learn about this cosmos, the more rich, complex, and marvelous it becomes, not the less. So the more you dig down, the greater our technology, the greater our apprehension or capacity actually to discover it. So we talked a bit about worldviews and paradigms, and among those things, we had this notion that somehow people suppose that science requires no faith, but actually all propositions, all forms of knowledge require certain preconditions of knowledge and certain assumptions that have to be made. You can't just say, I have no faith, but everyone has a measure of faith. It just depends on the object of the faith. So faith is only as good as the object in which it's found. So everybody lives by faith, number one. Number two, faith is only as good as the object in which it's placed. And so that's the second important thing. Now, there are many places where science could have developed but did not. And it's intriguing how it didn't form except in one place, and that was really in a context in which it was believed that the universe is rational and can be studied. It didn't occur in the East because the idea of the universe being an illusion would not really generate robust science, but rather in the context in which the Logos was an ordering mind. So there were technologies, very great systems and so forth, but not really a scientific and empirically based science based upon the idea that the universe has a rationality that our minds can correspond to that. And these progenitors of science, as we saw last time, from Copernicus to Mendel, were people who embraced that notion and actually believed that their doing science was compatible with their actual understanding of learning about the mind of the maker, so that it was not something that was inimical to faith at all. And so rather than saying it's one or the other, it's really to say that they both have to be seen together. But in the 19th century, there was a beginning of a movement that began to impose a naturalistic philosophy upon science. And so that the idea is that you now have to have a naturalistic assumption. And so methodological naturalism said you can't accept the possibility that there may be something beyond just what is materialism. And then it became a philosophical naturalism as well that was imposed on science. But that's not really what science is. Science should be defined, as it always has been, inference to the best explanation, go where the evidence leads. And that's called abduction, you see. Go where the evidence leads. What's the best implication or the best evidence for that? So I like to use for example, the idea of a turtle on a fence post. And that's what I was using before, you see. When you look at a turtle on a fence post, it's always intriguing. So you see something like that, and you have to ask yourself, what are the possibilities that are before you? So you see this little object here. What are your possibilities? Was it just happen to be there? Did it crawl up there? You know, that's not a good choice, you see. You know that it wasn't probably likely that a wind or a gust of wind blew it up there and made it there. The third possibility that someone actually put it there becomes the most likely and most plausible explanation. Inference to the best explanation means then that there was some intentionality behind that. And that's what we're suggesting here as well. So when you go where the evidence leads then, it becomes this mindset then that helps us grasp this concept of going where the evidence takes us. And we saw it before as well, that there are multiple kinds of science, evidences and knowledge. Because science is not just the thing that's the only form of knowledge. Sometimes people get really arrogant and suppose if it's not scientific, it's not knowledge. And that is really a lot of hubris, because it's not the case. Scientific knowledge is a legitimate portal of knowledge, and it has its own epistemology. Epistemology is a way of knowing, a logical entry point. But there are other forms with their own epistemologies as well. Michael Polanyi talked about personal knowledge a lot, and the whole idea of personal knowledge is not the same kind of a way of knowing a person that you would know a theory or a proposition in that sense. Historical knowledge has its own rules of engagement, as well as moral and aesthetic knowledge, religious and philosophical. So each one of these then has its own approach, and I'm suggesting that none are exhaustive. So you do not want one just to say, if it's not scientific, it can't be true. In fact, that statement is not a scientific statement. You see, just to say, if it's not a scientific statement, it must not be true, is not a scientific statement. You see, it's a self-defeater. It's like saying, I can't speak a word in English. You see, that's a self-defeating statement. I remember my friend Ray Musselman in college, he thought it was very profound when he wrote a sentence in a circle, and it was like a Zen koan for him. He said, this sentence is incorrect. Woo! So if it's true, it's false, but if it's false, it's true, and he thought it was really profound. It was just a self-defeating proposition. It was a stultifying statement. The design theory, we saw as well, that even the atheist Thomas Nagel admitted that science can't tell you the identity of the designer, but it could be scientific to say it could be that. Don't eliminate that from the outset. And we saw as well that there are different degrees, or there's a big tent here when we're looking at the idea of design itself. From the idea of some kind of a form that doesn't involve a personal agency down to the six-day creationism. It's a big tent. And so we're not really zooming in on a particular modality of creation in this discussion at all. But we're really saying, in this big tent, the issue is whether we are open to the possibility of some kind of a design inference, you see. And that's really what we're suggesting. And in fact, we are already aware, as we saw last week, that there are multiple sciences that distinguish design from accident. We're already aware of being able to do that. And so we could see various forms. We talked about insurance claim investigation. We talked about cryptology, artificial intelligence. Archaeology definitely requires you to discern, is this really an artifact that just appears to be designed, or is it really something that was an artifact that was humanly designed? We do search for extraterrestrial intelligence, looking for sequence of prime numbers. We do this as well with random number generation. And so the real issue isn't some kind of a creationism, but rather go where the evidence leads. So in this discussion of science, faith, and reason, I'm really very modest. I'm just looking at the scientific evidence at this juncture. I'm limiting myself to that. And so then as well, when I did this presentation a number of years ago, I was looking at certain predictions, and at that time it was all the rage to speak about junk DNA. It was an arrogant statement, because you see, the notion was, if we don't know what it does, then it must be junk. Again, it's an arrogant notion. How do you know that it's junk? Turns out that actually, the more we learned about it in the subsequent years, it turned out to be there are actually various systems and control systems that were actually various levels of ordered and operating systems within operating systems. And so it becomes actually much more elegant than people had previously supposed. It's like in your brain. We don't know what the glia does that much, but it's more profound than you might know. It's like you have as many glial material as you do neuronal. Yet we don't know much what it does, but I can assure you it's not wasted junk. It's doing stuff. And the more we learn about it, the more amazing it becomes. So in fact, we ought to be open to this idea and have a sense of humility to realize the more you learn, I don't care if it's a plant or a bird or an insect or a leaf, the more you learn about it, whether it's the microcosm, the midicosm, the biosphere, or the macrocosm, the more you learn about it, the more astonishing it becomes, not the less. And then deeper complexity, elegance, not less. And that's why I'm going to argue, and that's why I was saying, that there is a momentum of evidence that moves us toward greater complexity, greater elegance, and greater information. And so, intriguingly, as science and the instruments of science, our capacities increase, so also our capacity to see things we didn't even dream exist before. And so it goes more and more, not less and less. So we began last week, and again, a brief summary of the evidence for the universe's beginning. And we said that if anything now exists, it was this proposition. Something's got to be eternal, or something not eternal must have emerged from nothing. And so we said that these are your four options. Either it's an illusion, and some buy that idea. It's a pretty consistent illusion, though. You see, even the person who believes it's an illusion looks both ways before crossing the street. Or it's an eternal, and that was the main view, that steady state theory, or that it popped out of nowhere, or that it was created by an eternal being. And so we talked about the first possibility, which really wasn't a plausible option. And then the most popular idea, until quite recently, when it was actually defeated by new evidence, was that it always existed and somehow was being created, new energy at the edge of the universe. And that was a faith proposition that defied the first law of thermodynamics. And then the Big Bang theory was the idea that it couldn't have been eternal, that had a starting point. And so with more and more evidence and more material, microwave anisotropy probes and so forth, we discovered really strange things. And I'm not even going to hold to this because I'm pretty confident this will be later modified radically. So you have to be pretty careful not to hold on to the current cosmology, because if you do, you're going to be find yourself then, you get married to that, you're going to be a widower when that comes along. A new thing will replace that. Currently, the theory is that there's 73% of the universe consists of what's called dark energy, another 23% dark matter. Isn't that interesting? So that means that we don't know about 96% of what things are. We give names to it because we don't have a clue, dark energy and dark matter. But it is elegant. And so we go backwards then, we see the expansion rate of the universe and how strange it is, and there seems to be an initial point. And then that's complicated as well by the second law of thermodynamics. And the second law, which tells us that if you go back far enough, that there would have been a perfect point at which the total amount of energy had to be useful. How could that possibly be? You see, it tells us that as time goes by, the amount of useful energy diminishes, and it's on an asymptotic decay curve, asymptotically approaching zero, but so that it predicts the heat death of the universe. There won't be enough energy to sustain even the simplest forms of systems at all. And that would take a long time for that to happen, but it's not actually, it'll go out with a whimper, you see. And yet, if you go backwards, projecting backwards, it actually tells us there was a point at which the universe was wound up perfectly. And if there was any time before that, it had to be constantly all entropy, all loss of useful energy had to be replaced. And how could that possibly be? So there's fascinating material there. So the idea that the universe had a beginning is where we left off. And it relates to a measure of faith to really buy these things and try to understand what's going on. But we remember, again, what did I say about faith? Two things. It's only as good as the object in which it's placed. And everyone lives by faith. I mean, I get into an airplane, and I almost never look and see who's flying it. You know, I don't know, I haven't checked their credentials. It may be podunk airlines, you know. But generally you want to basically check that out. No, you don't really do that. You trust because there's some evidence that there is that. But how do I know who's flying the thing, you see? It may be some monkeys in the thing. But the point here is that you strap yourself in there, and you may not even know about the differential lift in the wings that causes the thing to lift off, even though it's heavier than air. But the fact is that it does work. And so we do have the idea of a faith proposition. And so, but there's faith founded on fact is the real issue. And that's where I'm trying to move us. And so now I want to talk a bit about the fine-tuning of the cosmos, and that's a second profoundly important evidence. And so here we go into the idea of the fine-tuning of the cosmos. And I always love the Starry Night imagery there as he painted that in Provence. Saint-Remy de Provence. I remember seeing that being there under that starry night in this wonderful place. It was right there where Nostradamus actually had his house, a very eerie place. And at nights when we'd come back, we'd go under the starry night, and there we'd see the very things that he was looking at there. It was a marvelous time to be there. But here we have just the right, that we are in a Goldilocks universe, and the more we're learning about it, the more it really does turn out to be just right. You see, the universe to sustain, even have the possibility of sustaining life, has to have just the right kinds of particles. And this is a massive discussion. The implications are enormous here. It has to have the right kinds of atoms as well. It has to have the right kinds of molecules. And we're just scratching the surface in our discussion here. And beyond that, it has to have the right kind of galaxy. Not any ordinary galaxy will do. It has to have the right kind of stellar masses. It also has to have the right expansion rate. And this is a huge theme because we discovered the expansion rate of the cosmos is exquisitely fine-tuned, as you'll see. Furthermore, it has to have the right kind of star. No ordinary star will do. It has to be almost exactly the perfect kind of star, which is the kind of star we actually happen to have. It has to have the right kind of planet. It has to have the right kind of moon. No ordinary moon will do, and it has to have the right kind of planet and the right kind of moon in that right ratio, in the right place. As well, you go on to realize, as we think about this, that the universe is more like a clock or like a watch that is really perfectly organized and really finely tuned. All the pieces are meshed together, perfectly sequenced in ways that go beyond what we ourselves would even be able to create, as we'll see. When Carl Sagan wrote about the cosmos, he predicted that we might have millions, he was very fond of the phrase billions and billions, but millions of habitable planets, even within our own galaxy. And at that time, there was only a handful of parameters that were seen to have a possibility of life. And since the 60s, dozens and then scores, and now hundreds of fine-tuning parameters have been discovered. And indeed, thousands of planets, exoplanets, have been discovered as well. But what's interesting is that the fine-tuning parameters keep going up. He was using the Drake equation that had about 20 particular parameters. But now there are literally hundreds, and they keep on growing every year. And that really is so intriguing that Fred Hoyle, who used to hold to the notion of a steady state theory, who revised his views because of new evidence, actually put it this way. He says, it appears like some super intellect monkeyed with the laws of physics and chemistry. It was so delicate and so perfectly balanced that he said a common sense interpretation suggests such an outcome. So we'll just look at a few of these things as an example of that in our time together. First of all, we'll look briefly at the strong nuclear force. I'm not going to go into detail, but just to explore a few of these parameters. How is it possible for there to be molecules, let alone life? There's just a possibility of that. You have to have just the right conditions. There have to be atoms, there have to be molecules, you have to have the perfect molecular bonding that requires just the right amount of electromagnetic force. And if they were a little bit larger or slightly bit smaller, you wouldn't be able to have atoms at all. They wouldn't bind. And so the ratio of the electron mass to the proton mass is exquisitely fine-tuned. Just the slightest bit more or the slightest bit less. And you wouldn't have any atomic material at all. And so it has to be very, very tightly, that ratio is very tightly controlled. And the strong nuclear force also has to be an extremely precise quotient, you see. If there were just a tiny portion of a percent more or less, you couldn't have life, because you couldn't have molecules. So all these conditions are necessary for that as well. So we keep on discovering these things. With the weak nuclear force, which has to do with the nature of radioactive decay, that's the same condition here. We're discovering that that too has to be finely tuned. Any more or any less, you couldn't have stars, you couldn't have galaxies. And we've discovered more and more such fine-tuning parameters. The universe, with its constants, its laws, and its initial conditions, requires exquisite balance to produce a relatively stable environment, which makes life possible. So all these various components, the perfect ratios, all these things fit together. The neutron is another example. The force of gravity is extremely refined. And if the neutron were just 0.1% more massive or less massive, you wouldn't have the elements necessary for life. And then another way of looking at it, here's going to be one example of this, is considering our US government debt. And if I compare this, I'm going to make an analogy using, how would I describe the probability of 1 chance in 10 to the 37? And the reason why I'm coming up with 1 part in 10 to the 37 is that is the mass ratio of electrons to protons. The mass ratio of electrons to protons must be so finely tuned that if there's any change less than 1 part in 10 with 37 zeros after it, you could never have actually any kind of life or any kind of materials at all, because you wouldn't bind. It just wouldn't work. So just to give you an idea of what this particular probability would be, Hugh Ross came up with an interesting description. A vivid analogy. Imagine that you have the government debt, which is an increasingly depressing topic. And at the time he wrote this, it was a lot less than it currently is. At that time, the amount of money to pay for that debt would require 1 square mile of dimes, which was less than 10 feet deep. 1 square mile less than 10 feet deep. So I'll let you do the necessary adjustment. Maybe a few more square miles, who can say? But it's not that huge in comparison to what we're talking about here, because now, imagine though you now took not 1 square mile, but the whole area of the United States, but not 10 feet deep. Instead, make it so deep that it would actually go up to the height of the moon, 237,000 miles. So you've got that area of square miles going all the way up to the moon, and now multiply that by 1 billion times. So you have 1 billion piles of those, you see. So you're getting the figure here? So you have 1 billion of those piles, and your job now, one of them has been marked in those billions of piles with 1 dime marked red, and your job is to find it. You see, that's the probability of 1 part in 10 to the 37. I wouldn't put my money on it. It gets worse after that, because the expansion rate of the universe is worse than that. That's 1 part in 10 to the 55. That number is so incredibly inconceivable that the best you can come up with it, as one person put it, is perhaps thinking about so minute. Imagine a smooth glass surface and a pencil. Smooth glass surface and a pencil. Your job is to balance the pencil without any external forces, with its point standing up. Now multiply that by 1 million, and you approximate 1 chance in 10 to the 55. Are you with me on that? And yet that we know is the expansion rate. One change in 1 part in 10 to the 55, we wouldn't be here, because we would have a cosmic crunch or cosmic expansion to where we couldn't actually be here at all. So the precision is such that it would be a crunch, or it'd be spun off so fast that you wouldn't even have galactic formation. Stellar mass is yet another example of this. And so when we consider stellar mass, if the ratio of the electromagnetic force to the gravitational force changes by 1 part in 10 to the 40th, 1 part in 10 to the 40th, and that's, again, 1,000 times worse than what I gave you before for the United States, that example. 1 part in 10, you would either have only small stars or only large stars. You wouldn't be able to have the middle-sized stars required for life, you see. That's the fine-tuning required for this. So it's extremely tight. Moreover, you have to have just the right kind of galaxy as well. Not any galaxy will do. It has to be a spiral galaxy for various reasons. An elliptical galaxy will not serve, nor will an irregular galaxy serve. So only spiral galaxies provide any what so-called safe zone for life-sustaining planets, you see. And so it turns out that about 20% of the galaxies are spiral galaxies, and about 60% are elliptical galaxies, and then the remaining 20% are regular. And so that's yet another component of it. Oh, I didn't mention that, but there are also these habitable zones. I'll tell you about that in just a moment. Our just right sun. You have to have just the right kind of sun. It has to be a yellow dwarf. And so it's the right kind of light. It emits a balance of red and blue, which allows photosynthesis. It has to be the perfect combination of light. The right composition with a high metallicity for creating terrestrial planets, you see. As well, you have to have the right orbit, nearly perfectly circular, almost circular, for the temperature stability. It also has to be a single star system and have the right luminosity and stability and so on. So when you go and you see Tatooine in Star Wars and so forth, it wouldn't work. You can't have life on a multiple star system. For very good reasons why that wouldn't work. It has to be a single star. So there are various components of that as well. Then in addition to that, it has to be there is a circumstellar habitable zone. This is certainly not to scale. And so what you have here, the Earth must be just the right distance from the sun, plus or minus 5% distance to be exact. Too close, whoop, I went too far. And let me go back to that for a second here. Go back to where I was here, and go back to there. So if you go too close to that distance, what would happen then is that you would boil off the Earth's oceans too far, and water and carbon dioxide would freeze, and you'd eventually develop runaway glaciation. So there's a similar narrow pathway there, very narrow area there as well. I might point out as well that there's a circumstellar habitable zone, but there's also a circumgalactic habitable zone as well. So that it turns out that within our spiral galaxy, there's only a very small region where there could be possibility of life in the galaxy. Because if you get too close to the galactic center, the radiation would be too intense, you see. And there are other reasons why, and you wouldn't have the metallicity if you go too far out. So there are various reasons. And so there's a galactic habitable zone. We happen to be right in the center of that habitable zone, about 4%. And so, again, yet another fine-tuning parameter. These parameters just keep on multiplying, you see. And I find that to be quite intriguing to see and to imagine what that's all like. And so when we look at that then, we see these extraordinary things and themes that go on. going back to where we were then. So we see as well, if we imagine then, if we take, there are hundreds of these parameters then, and I'm just going to be very conservative here. I'm just going to limit myself, but there's the ratio of matter and antimatter is a very highly restrained thing. It's got to be precise. If these things change in the slightest bit, we couldn't have our discussion here. The precise quotient between expansion energy and gravity is yet another one. The expansion energy of the universe and the gravity, the right ratio. What's called the resonance energy of carbon has to be in a very narrow range. Also, what's called the mass density of the universe, a very tight range. And also, the cosmological constant is very tight. So if you keep on adding these increasing numbers of parameters, and they will go up, they'll continue to grow up, the more we see, the more we realize we're in a Goldilocks universe. It's just right. A very, very conservative estimate of the probability of having a universe with just a fraction of the right constraints, where you could have the possibility of life. We'll just make it 1 part in 10 to the 215. It's actually far, far worse than that, far more than that. But I'll be conservative. 1 part, I'm being very generous. 1 part in 10 to the 215. Now, suppose we have a generous estimate of planets, exoplanets. We know that there are many exoplanets. Let's make it 10 to the 22. That's more than any typical estimates would be. Again, that's one with 22 zeros after it. So I'm being generous. But now what you do is you subtract 22 from the 10 to the 215. Now it brings us down to 1 part in 10 to the 193. But what we're dealing, whenever you're dealing with a probability in excess of 10 to the 50, you might as well say 0. Possibility. You see, you're getting to that point here. So I'm suggesting here that we're dealing with it's becoming increasingly evident that it may have taken a universe this big and this age to create a context in which we could even be here having this discussion. Now, I remember Jodie Foster looking at the cosmos and saying, what a waste. All those stars, all those galaxies, what a waste if we're the only ones. What if, let's take a different point of view. What if it took all that to have the conditions where we could have this one discussion? It's a totally different point of view. The privileged planet. And what I'm suggesting is we really do seem to have won, quote, the cosmic lottery. This is basically the whole anthropic principle that's been described here. And the bottom line that we're dealing with here is that that there's an elegance and a fine-tuning that's so extraordinary that people have been desperate to avoid the obvious implications that it would seem to suggest that this couldn't be random. Imagine, for example, you go to Las Vegas and you watch somebody, and he keeps winning, and he keeps getting, royal flushes, and say he has there's a 6-deck shoe that they're being dealt from, so he's got this, and he keeps on winning and winning and winning. After a while, wouldn't you get a little suspicious when he keeps getting another one and another one and another one? You'd think that the thing was loaded. You see. Or suppose another person has a fair coin, and he keeps tossing the fair coin, and he gets tails every time. Now, you might suspect that it's 50-50 chance every time, of course, you know that. But after about 10, and it gets 10 tails in a row, then 20, then 40, you know something's fixed here. Something can't. What's your best chance, probably? The game's been fixed. Something's wrong, you see. It can't be this way. And so one way of getting around it is to suggest then that either there's some agency involved here, or you know that the probability is 0. And so one way around it, here's a workaround. Give me an infinite number of universes. That's the workaround. Yeah, give me a multiverse. That'll be my solution. Yeah, that's the trick. That's the ticket. Give me an infinite number of universes, and because we're having this discussion, we must have won the cosmic lottery. See how it works? But here's what's interesting. In order to develop multiverse theory, you have to defy the first and second laws of thermodynamics, which are the two most fundamental laws of physics, in order to embrace that, number one. And number two, you don't have any empirical evidence by definition to embrace it, because one could not actually be able to be ascertained from another. There'd be no empirical warrant. So in defiance of all empirical evidence, based upon your desire to avoid the obvious implications of this Goldilocks universe, you're willing to deny the two most fundamental laws of all physics in order to embrace your view that we have to get an escape workaround to avoid the idea that there may be a creator, one who made it. You see, who's living by faith now? You see, so for me, that becomes problematic. It's inference to the best explanation. So I have a real problem with that. So I go back to where I started, inference to the best explanation. So we have Mount Rushmore. And I had an opportunity to go there. I was invited to speak at the governor's prayer breakfast in South Dakota. And I took it for two reasons. There was one of the two states in the Union I hadn't been to. And so now there's only one out of the 50 I haven't been to, and that's North Dakota. So if I'm ever invited to go to Fargo, or Bismarck, I'm going to take it just to write it off. But the other is I always wanted to go to Mount Rushmore, you see. And it's fascinating to see that, but you can begin to see, of course, when you look at the Black Hills of South Dakota, in tribute, of course, to natural causes, except for these four presidents these likenesses seem to be there: Washington, Jefferson, Roosevelt, and Lincoln. And that implies design, and so I would suggest then that that area was not a matter of erosion, you see. And in fact, we happen to know who the guy was who designed it, Guston Borglum. And so we're looking at the idea. He used a simple multiplication of plumb line to transfer his measurements to a scale model. And again, we're back to this concept then of what would be the best way of understanding that. In fact, that's why I love this kind of a thing, because I love these things with rock cairns, you know, for example. You see these things. If you were to see a rock cairn like this by a stream of water, what would you conclude? You can see that. Yeah, it's possible that this happened to be there. I wouldn't put my money on it, you see. I particularly like this Pontus Jansson. This guy, he has videos of them, and he makes all these cairns, and he actually shows them. And it's amazing to watch him create these things. They're marvelous. He balances these things without any glue or anything like that. He has a genius for making these wonderful things. But I can pretty well promise you, if I were to see one of these things out there in nature, I'm pretty confident I wouldn't make the conclusion that this just happened to be there. But I want you to note something about this. This is trivial, child's play, simplicity compared to any of the simplest cells or features that we see in the universe. In fact, when we look at that, we say, oh, somebody put that together. Let me suggest, though, that the butterflies that are there are infinitely more complex than the design that created that. So it's impressive to me when we see this. So when we go back to this idea then of looking at inference to the best explanation, next week we're going to look at the origin of life. I argue then that we see that science really is a powerful resource to help us to begin to realize that it is, in fact, you don't have to put your brain on the shelf before you open the Bible. You see, it's consistent with the science, faith, and reason. They go together. And so the one who made all things is the one who made your mind and gives you the capacity to resonate with the things that were made because you bear that image. Let me close in a prayer. Father, we thank you for this time together, and we're asks that you give us wisdom and prudence, discernment and understanding, and greater appreciation for who and whose you are, that the Logos who made all things became one with us. Pray in his name. Amen.